We're going to examine the transformation of functions, particularly for our absolute value problem. So up here highlighted right now in purple is our parent function. So our parent function of an absolute value takes on the shape of a V, and any absolute value function will take on a shape of a V. If you look down here at the function that I just now highlighted, that is our transformation. So what we're going to examine is what effect does changing the coefficient of A in front of the absolute value have on the shape of our graph? What does changing the value of H have on changing where our graph is in space? And the same thing with K. If we notice, if I just move this little slider on A, how it makes the function get really narrow, or how it makes the function flip. It also makes it get wide. We can see right here it gets wide. The green V is our parent function. So I'm going to put this function back on top of the parent so it's just the same as the parent. But now I'm going to shift the function. I'm going to take H and I'm going to shift it. And you can see how H is moving my function left and right. And I'm going to do the same thing for K. I'm going to move K, and you can see that K is moving it up and down. So this would be a vertical transformation. This is a horizontal transformation. And this is my stretch or my compression, so it gets wide, or my reflection. So you notice I don't have any axis showing at all because everything is just being compared to where the parent function is. So let's look at our function on the xy coordinate plane. So right now I'm just examining my A. My A is in front of my X, as we can see here, in front of the absolute value. So I'm going to show my parent function. Excuse me. If you can see, excuse me, my parent function is right here. Right now, my A is 0.5. Right there, it's 0.5. So that's making my new transformed function compressed. It's wider. My vertex is right here, the same as my parent, at 0, 0. So notice my H is 0 and my K is 0. The other thing is my axis of symmetry is actually right here. You can't see it on here because it's, let's see if we get it to show. Oh, there it goes. My axis of symmetry is right here. It goes through my vertex, and that's where x equals 0. So let's see what happens. Let's change this A. Let's make this A a 1. So if I make A a 1, notice that my function is lying right on top of my parent function. My vertex has not shifted. My axis of symmetry is still the same. Let's make A equal to 2. Notice how my function has gotten narrow. It's stretched towards my y-axis. Let's make it 3. My A is now 3. It's gotten even narrower. Let's make this -2. So now my A is -2, and my function has reflected over the x-axis. Notice my vertex has not changed. My axis of symmetry is still the same. The only thing that's changing is if this is flipping over the x-axis or if it's getting wider or narrower. So right now we have a reflection over the x-axis as well as a compression. If I make this -3, we can see how it's moving in closer and closer to the y-axis. Let's make it a -4. It's even closer in. If I make it +4, notice how it's reflected over the x-axis. I can make this 1/4. Notice how it's gotten wider, it's compressed. So that's simply what the A is doing. The A is simply either stretching, compressing, or reflecting my function. So let's look at a horizontal shift. So notice here, in the function I'm showing right here, that my A is 1. So 1 times anything, but you don't need to show the 1. Right now, my H is -2. So let me show you the vertex. So my vertex is at -2, 0. But the thing I want you to notice is that this part of the function right here is a negative times a negative. So a negative times a negative is going to make that a plus. So this is going to be the same as the absolute value of x plus 2. Because what my x is here is going to be opposite in my vertex. So it's shifted to the left 2, even though it's the absolute value of x plus 2. Okay, so let's go ahead and let's make this h a plus 2 and see what happens. So notice that my vertex has shifted to the right. My vertex is now 2, 0. My equation is the absolute value of x minus 2. That minus is part of the equation. So my vertex is opposite of what I see here. So if I make this a 3, it just shifts it further to the right. Remember, I'm comparing it to my parent function, which is right there. So it's gone to the right 3. If I make my h -3, again, look at my equation right here. I have a negative times a negative. A negative times a negative makes that a positive. So the function is the absolute value of x plus 3 is how I would end up writing that. But notice my vertex is at -3, but inside my function I have a positive 3 inside the absolute value. My A is staying 1, and I don't have a K. My K is 0 right now. It's been staying 0. So let's see what K does. So let's go to vertical shift. So if I go to vertical shift, notice that I have a plus sign right here. That plus sign means that whatever my y value is at my vertex, it's going to be the same. So if I show you my vertex, here's my vertex. Notice that my y value at my vertex is 4. So in the function, it's still positive 4. If I change that y to put it -4, what's going to happen? Notice how my function shifted down. And again, we're going to compare it to the parent function. So here's my parent function. My function, the vertex, shifted down 4, -4. Notice this is -4. Notice my y value in my vertex is -4. Because a positive times a negative is a negative. So that's just going to stay -4 on the outside of the absolute value. Let's go ahead and let's put the two together. So here I have my h, and here I have my k. So right now my vertex is at 2, 0. So let's look at the function here. Notice this is minus 2, but my vertex is positive 2. Compare this to my parent function. My vertex has shifted to the right 2, opposite of what I see here, which is showing me as a minus 2. So let's change my h to a minus 2. Remember, my h is my x-coordinate of my vertex. So we can see that now my vertex has shifted to the left. And again, notice that this equation here has a minus times a minus right here. So that means I have the absolute value of x plus 2 is how that gets written. X plus 2, and of course plus 0 doesn't add anything to the equation at all. So that would be what this function is. So notice that inside the absolute value I have a plus 2 that corresponds to my vertex of my x-coordinate, which is minus 2. It's moved my function to the left 2. Let's go ahead and change my k value. Let's make my k value 4. So notice that my k moved my function vertically 4. So for this particular function, I'm going to write it out right here up above. If I'm going to write this out, I'm going to have my f of x is equal to the absolute value of x plus 2, close my absolute value sign, plus 4. So this plus 2 moved my vertex from the parent function to the left 2. And this plus 4 on the outside of the absolute value moved it up 4. My a is staying the same. I haven't done anything with the a. Notice my a is still 1. My axis of symmetry is always through the vertex. So my axis of symmetry is the line where x equals negative 2, because that's the x-coordinate of the vertex. So we could go ahead and do all the transformations together. So here's the entire equation. So let's show the vertex. So notice this says minus 2 for my h inside. That means that my h at my vertex is 2, opposite. Okay? And my k is 0. Let's change the k. Let's make the k a negative 3, which means my whole function shifts down 3. Remember, we're comparing this to the parent function, which is right here. And then let's switch my a. Let's make my a 2. So if I make my a, this number right here in front, 2, notice how it makes the v narrow. If I make it negative 2, it reflects my function over the x-axis. Let's make this a fraction. Let's make it 1/2. So notice with it 1/2, it made it wider.